In this video, we'll be looking at the logarithm unit review. So I'll be doing a bunch of example problems that you can find similar on your review packet to try to get ready for our logarithm unit test. So to start out, first thing we're going to talk about is rewriting an equation in logarithmic form. So usually if you want to get it into logarithmic form, it's in exponential form. That means you have some kind of base. The base on this one's 3. It's been raised to the second power, that's the exponent, and then it equals 9. That's the solution. That'll be the argument on the logarithm. So if I want to convert this to logarithmic form, I always start with the base. Base on this one is 3. When I write this in logarithmic form, it's going to be log base 3. And then I take the 9 and the 2 and I just switch their positions. The 9 it becomes the argument, or what's on the inside of that logarithm. So this is read as log base 3 of 9, and that would equal 2. Another example of this would be 5 to the negative third equals negative 5 to the negative third equals 1 over 125. So if I want to just rewrite that in logarithmic form, I start with the base. Base on this one is 5, so it would be log base 5. And then I just switch the position on the negative 3, the exponent, and then the solution, it becomes the argument. So we have log base 5 of 1 over 25 would equal negative 3. Once we know how to convert from exponential to logarithmic form, we want to be able to go backwards. So if I'm given a logarithmic equation and I want to rewrite it back into exponential equation, I do just the backwards operation of that. I still start with the base. The base on this one is 5. 5 is the base on this logarithm, and so it is log base 5 of 25. And then, of course, that equals 2. So if I convert that to exponential form, the base would be 5. I would raise it to the second power, and then that equals 25. Another example of this, if I had log base 10 of 1,000, if you don't see a little base number written there, then 10 is the base. But log base 10 of 1,000 equals 3. So if I convert that, the base is 10. It would be 10 to the third equals 1,000. So 10 to the third equals 1,000 is the converted form of that. And now we'll take a look at a couple examples where they'd like us to evaluate this expression without a calculator. So I want to try to figure out what that logarithm would be without a calculator. So it is log base 7 of 49. Now remember, what a logarithm is doing is asking how many times that base is being multiplied into the argument number. So that 49 is really 7 times 7. So I'm going to go ahead and write that as 7 times 7, or 7 squared. So I have log base 7 of 7 times 7. Which is also log base 7 of 7 squared. And so since the base is 7, and really a log is asking how many times does that get repeated, well, that 2 is counting how many of those are there, and so this would just be 2. So the solution to that logarithm would be 2. If you wanted to, let's say, set this equal to x, and then convert it and think about, okay, well, that would be 7 to the x power equals 49. And 7 to the second power would equal 49. So that confirms that for us. So another example here would be log base 6 of 1 over 36. I want to try to figure out how many times that this 6 right here, that's the base, goes into 1 over 36. Now 36 is really just 6 squared. So I can rewrite that as log base 6 of 1 over 6 squared. And then I can move that 6 squared to the numerator, or to the top. If I do that, that would be log base 6 of 6 to the negative second power. And once again, this logarithm is counting how many times that is there. And this says there are negative 2 of those. And so negative 2 is the solution for this one. In the next problem set, they ask us to use a calculator to approximate each log to the nearest 1,000th, or thousandth, so 3 decimal places. And we're going to have to use the change of base formula to do this. So if we have log base any b, whatever the base is, of a number right there, to use the formula on our calculator, we have to go log of whatever the argument number is on top, and then log of the base on the bottom. So we have to do that ratio every time we want to put that on our calculator. So if I want to figure out what log base 3 of 7 is, let's say, first would use the change of base formula so that I can put it on my calculator. My calculator only has base 10 and one other base, base e, or the natural log, but we're going to use base 10 for all of these. So this would be log base 10 of 7 over log base 10 of 3. Remember, if I don't write the base number on that log, it's automatically base 10. Okay, so we're going to put that on our calculator. We're going to go log of 7, divide that by log of 3. So let me put that on my calculator. So we're going to go log of 7. Oops. Make sure that you close out that parenthesis after the first log, otherwise you won't get the right answer. So we're going to go log base of 10 of 7, and then divide that by log base 10 of 3, and looks like we get 1.7712. So if I go back to this, that should be my answer for that, 1.771. One more example of this, log base 6 of 15. I'll use the change of base formula. I always think the base goes on the bottom, so it would be log of 15 divided by log of 6. And once again, just throw that on your calculator. Slide this over. So we're going to go log of 15. Make sure you close that parenthesis out, and then divide this by log, oops, forgot what the base was, 6. Log of 6. And so I get 1.511 for this one. So 1.511 for that. In the next section, it asks us to expand a logarithm. So there are 3 properties that you have to know for expanding logarithms. There's the product property, the quotient property, and then the power property. So we have those 3 properties. I wrote them up here in the top right-hand corner, but if I'm multiplying what's on the inside of the bases, the x and the y, I basically get to give each of their insides, they get their own logarithm, and I'm going to add those together. If I'm dividing, or the quotient rule, then I subtract the 2. And if I have, let me get that rid of that, and if I have a log of a base that's being raised to a power, or an argument that's being raised to a power, that y gets to sneak into the front. So it becomes like a product of it. So the y we can just slide in the front. So if I want to work on one of these, expanding this logarithm, it's a condensed log. Let's say I want to expand that out. The first thing I usually do is either step 1 or step 2, or property 1 or property 2, depending if I'm multiplying or dividing. So this one I'm using the quotient, I'm dividing. There's a fraction on the inside of the log right here, and so I'm going to use the subtraction property first. So that says give each one its own log, and then subtract those 2. So the 7 to the third, 6 squared, each get their own log. Once you've done that, you can take the exponents that are on the argument and move them to the front. So log base 10, I didn't write the base, log base 10 of 7 to the third, that 3 can move to the front. So it'd be 3 log of 7 minus 2 log of 6. And of course I could put the original equation, this, on my calculator, or I could put that on my calculator, and I would get the same exact value for both of those. So one more quick example of this. This one is a product, so I'm multiplying on the inside of these 2. And so first I want to split that up for each of those terms. Since I'm multiplying on the inside, I'm going to go ahead and add those together. So it'll be log base 3 of x to the 5th plus log base 3 of y to the 7th. So I always do first step 1 or step 2, rule 1 or rule 2 first, and then I go ahead and look for that third rule. Does it have a power, and can I slide that power to the coefficient? So the 5 and 7 I will move to the front of their corresponding logs. So that would be your final answer. If I'm condensing logarithms, I'm going in the backwards direction of the last one. So expanding, you want to try to make it as expanded as possible, make each internal log simple. On condensing, we're trying to get it down to 1 logarithm. Sometimes one version is better than the other, just depending on what you're solving and how you're solving it. So this one is already expanded, and I want to work backwards to condense this. I want to get this down into 1 logarithm if I can. So first thing I would do is actually the third rule here. If there is a coefficient in front of the log, I just want to move it up to the exponent. If I can. So the 12 and 3 are coefficients for those logs, and so I will move those up to the exponent. Log base 2 of x to the 12th plus log base 2 of y to the 3rd. And then I just decided, is it adding or subtracting? If it is addition, then I'm going to make it the product of those inside arguments, and I can put those inside of 1 logarithm. So log base 2 of x to the 12th, and then multiplied by y to the 3rd. It is the product of those 2. One more example of this. 25 log, I didn't put the base there, x minus 9 log, didn't put the base there, y. If I don't put the base, it's automatically base 10. Just keep that in the back of your mind. So I'm going to take the coefficients and move them to the exponents. So it'd be log base 10 of x to the 25 minus log base 10 of y to the ninth. And then I'm subtracting those on the inside, and so I'll make that a quotient on the inside of 1 log, so a fraction. So it'll be log of x to the 25th all over y to the ninth, so a quotient between those two. In this next section, we'll be solving either exponential equations or logarithmic equations. So this one is an exponential equation. So to get that x out of the exponent, I have to convert it to logs. That lets me switch the position on the x in the 44, if you will. So this one, the base is 20. So I am going to write this as log base 20 of 44 equals x. So I always try to get the base and exponent by itself. Once I do that, I can convert that to a logarithm. So I'm going to put that on my calculator and see what that is. 20 doesn't really go into 44 multiplied very well, so it's going to be some weird decimal, but I'll use the change of base formula on this one. I'll go log of 44 divided by log of 20. Remember, I always put the base on the bottom when I use the change of base formula. So I would put that on my calculator, just like that, log of 44 divided by log of 20. So let's go ahead and take a look at that real quick. So log of 44, make sure you close that parenthesis out, and then divide that by log of 20, and it should give me 1.26. So 1.26. 32 is the value for x. Let's take a look at one more, little more complicated example. This one, the exponential equation, the m is up in the exponent, but the base is 7. I have to get that 7 and the m all by itself first. So I need to get rid of that 4. Before I convert this to logarithms. So I'm going to go ahead and add 4 to both sides, and it'll be 7 to the m equals 63, and then I'll convert that to logarithms. So it'll be log base 7 of 63 equals m, and then I will use the change of base formula, so log of 63 over log of 7, and then of course throw that on my calculator, and I would get 2.1292 In this next equation, it is an exponential equation still. I do have this 7 to the x power, but I've got some extra stuff. I've got a -8 and a +4 that I have to get rid of those two first. My goal is really to try to get this 7 to the x. That's the exponent, the base and the exponent. I want to get that by itself first. So you need to basically undo PEMDAS to get rid of that. So the first thing I would do is just add 4 to both sides. That would get rid of the 4 component, and then I have to get rid of that -8. Since it's being multiplied by 7 to the x, I can just divide it on both sides to get 87 over 8. And of course, those negatives would just cancel each other out. Once I get the 7 to the x by itself, I can convert that to logarithms. So it would be log base 7 of 87 over 8, and then that equals x. And then, of course, we're going to use the change of base formula. So log of 87 over 8, and then remember the base always goes on the bottom. So divide that by log of 7. So I'll put that on my calculator, and I should get 1.2264 on my calculator for that one. In this next exponential example, I've got a 7 to the n up in the exponent right here. It's not just a basic variable, it actually has a 7 multiplied against it. So I'm going to go ahead and worry about that last. I still want to get the base and the exponent all by itself. So I do want to get this part, 12 to the 7n, all by itself. So we do just want to move that 9 onto the other side. And so we'll slide that 9 on the other side to get 12 to the 7n equals 68. And then once we do that, now we can convert that to logs. So log base 12 of 68 equals 7n. And then now I can worry about that whole 7n. I can divide both sides by 7. Now I still have to do change of base on that left side to get that 1.698. That's log of 68 divided by log of 12 on your calculator. Once you've done that, you can divide both sides by 7 to get 0.2426, and that would be the solution to that equation. So if you have extra stuff in the exponent, just do that at the end after you've gotten it out of that exponent. So in this next example, it's got a lot of steps. This is the most steps that we're going to give you. We've got a couple steps on the outside and a couple steps on the inside of that exponent. I still want to try to get the base all by itself. So that's that 6 to the 10x plus 6. So I'm going to go ahead and get rid of those 3's first. So let's go ahead and add 3 on both sides. Reverse PEMDASing, I want to do any easy add and subtract that I can. Work my way up. Now I'm going to look at multiplication and division. Looks like I can divide both sides by a 3 to get 6 to the 10x plus 6 equals 33. Once I do that, I can convert that to logs. Once again, start with the base. So it's log base 6 of 33 and then equals 10x plus 6. We're swapping the order on the 33 and the 10x plus 6. So I will use change of base to figure out what log 6 of 33 is, and then which is 1.95. And then that's pretty straightforward to solve from there. I'll just subtract 6 on both sides, and then, of course, divide both sides by 10. In the next problem set, we'll be solving the equation again. This time it's a logarithmic equation, so it starts with a logarithm, and we're trying to figure out what x would make this equation true. So if it is just a base logarithm, you can just convert it to exponents to get that x out of the logarithm. So the base is 4, so we're going to write that as 4 to the third equals the x. So the base always is the base, and we swap the other two's numbers positions, if you will. So we just figure out what 4 to the third is. That's 64, and then that would equal x. So if I had one that was a little more complicated, log base 8 of m plus 1 equals negative 1, I want to try to get the logarithm by itself. So my goal is to get the log and anything inside it by itself. So this is what I'm trying to isolate. So I need to get rid of this plus 1 business right here. So we're just going to subtract 1 on both sides for this one. So that'd be log base 8 of m equals a negative 2. And then once I get the log by itself, convert that to exponents. So 8 is the base, so it'll be 8 to the negative second power equals whatever's on the inside of the log. So this time it equals m. And we just figure out what 8 to the negative second power is. Negative exponent, you can move that to the denominator, so it's 1 over 8 squared. And then, of course, 1 over 8 squared is 1 over 64, which equals m. And in this problem, they have a step on the inside and the outside of the log, but we have log base 2 of n plus 7. That n plus 7 is inside that logarithm, and the plus 2 is not. And then, of course, equals 5. So if I can do any add or subtract on the outside of the log first, I will. So I'm going to go ahead and subtract 2 onto both sides. So log base 2 of n plus 7 equals 3. Once I get that log all by itself, I just convert that. So the base is 2. So I would write that as 2 to the third equals n plus 7. So 2 to the third is 8. And then I can easily solve that for n. Just subtract 7 on both sides. And then 1 would equal n. One more quick example of that. Log base 3 of 4x. Take away log base 3 of 10 equals 2. So this one, I have multiple logs, but the good thing is I can condense those logarithms together. I can use my property rules to mash those logs together. So what that would look like, since I'm subtracting, I'm going to make this a quotient. So it's going to be log base 3 of 4x over 10. That's the quotient inside of one logarithm, and then, of course, equals 2. So I can get 2 logarithms and mash them together with condensing. Once you do that, just convert that with exponent to exponents. So the base is 3, so it would be 3 to the second power equals the 4x over 10, or that inside component. So from there, just solve it algebraically however you have to. So it looks like 3 squared is 9 equals 4x over 10, and then I would multiply both sides by 10 to get rid of my fraction. And then 90 equals 4x. I'll just divide both sides by 4, throw that on my calculator, and then I'll get 22.5.